Okay, welcome back.
Lecture 404.
Um, so in this talk, I'm going to focus on a sort of slightly different aspect of the questions we've been talking about, which is really focusing in on how parameter space comes into the picture. So we have this,
right? Parameter space, and like each parameter gives you a function, but we haven't really talked yet about like sort of that relationship.
So here's sort of the rough outline of the talk. Actually, there's a couple more sections I added that are not on here. But we'll start with sort of a motivating question, and then we're going to define fibers, and then we're going to get into some of the topology. Where's the clicker? Oh, thanks. Okay. Great. Okay. So the sort of overarching question for this lecture is if you're training a neural network, which functions is it likely that you will select by training? So let's just briefly review the training process. So you start with some data, input and output pairs. You pick a parameterized class of functions. So theta is your parameter. It lives in parameter space omega. You have some function that is your loss function or error function. And for each parameter theta, it tells you sort of how badly the function f theta matches your data. You initialize randomly somewhere in parameter space, and then you do gradient descent, sort of taking a sequence of discrete steps through parameter space, and you stop when you get to a place where your error stops decreasing. So in this kind of setup, it's great. It's convenient. There's a convenient picture, which is that we think of the parameter space as really being the space of functions. At least that's kind of how it's very tempting to think of it. Like you step through parameter space, and every time you take a step, you're really stepping to a different function. But sort of implicit in that is sort of the idea that your parameter space is actually like a good model for the space of functions. Yeah. Yep.
Other alternatives to gradient descent. I mean, I think everybody just always uses some form of gradient descent.
Greg, do you have any? Yeah. Yeah. Right, but like some form of gradient descent. Yeah. 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 Okay. Yeah. Great. Thanks. Okay. So we would like to understand sort of the so-called dynamics of training, meaning like, what's likely to happen when you do this process. And there's a bunch of reasons for this, many reasons. Here are a few. I mean, well, first question is like, how can we even how can we make this training converge to a function or a parameter that actually like fits your data pretty well? Can we make this training process more efficient? It's very computationally expensive. Sometimes you try to train and it just kind of doesn't get to anything that's useful. So second question, we touched on this a little bit before, but interpretability. So how can you understand why your trained model does what it does? And so sort of in that direction, what properties is the trained model likely to have? Why does it, work the way it does? And then another sort of motivating question, which I mentioned previously, is over-parameterization, right? So as I said previously, it turns out in practice that often the models that train really well have way more parameters than there are data points. And our sort of current understanding doesn't fully explain why this works. So all of this you can kind of lump under the category of like dynamics of training. Okay. And so this is a picture I showed earlier, which I should say I stole from the internet. It's not mine. I apologize for not giving credit. But right, so the idea is like people talk about the loss landscape, right? So you have like your parameter space theta, and you think of the loss. So the loss is the vertical direction in this picture, and you just randomly initialize somewhere and you walk downhill. And so this is sort of a mental model for what's happening. And this is a lovely picture. And what I'm going to spend the rest of this hour or so convincing you of is that this is a lie. It is a beautiful lie. Okay. All right, so that's the intro. Part two, I'm calling this fibers. So first, I'll start by defining the map that I'm really interested in. So definition. Suppose you've got one of these parameterized function classes, f. What I'm going to call the realization map is the map that goes from parameter space to the space of functions. And I'll use rho because rho starts with r, and you're like realizing a particular function at a particular parameter. So it just takes your parameter and it gives you the corresponding function. So now we can define the fiber of this map, or actually the fiber of any function. Oh no, sorry. Yes, with respect to this. So you've picked a family of functions, script f. The fiber of some function g, it is, I'm going to denote it by rho inverse of g. And it's just all the different parameters, theta, for which f theta is the function g. This is the preimage line fiber. So that is two different parameters are in the same fiber exactly if they give you the same function. So we're starting to think about why training works the way it does. This is an important notion because if two functions are the same, then regardless of what your data set is, your loss function will give you the same error. So as we start to think about this, this picture, if we have two parameters that give you the same function, yeah, they'll correspond to the same height or elevation. Questions about fiber? Just the definition. So this is almost the take-home message of this talk, that for these parameterized function classes that are used in deep learning today, the realization map is not injective, meaning that fibers are usually not just a single point, but a whole manifold of points. So there's like lots of different parameters that give you the exact same function. And this is like very different than some of the families that we're used to thinking about, such as the family of polynomials of some fixed degree. So like for a family of polynomials of degree d, the realization map would like take a bunch of coefficients, the parameter, and just give you the polynomial with those as the coefficients. And so in this case, the map is injective, right? Because if you have different constants, they're going to give you a different polynomial. Or another way to say this is that the fibers of the realization map are trivial. They consist of single points. And the other nice property in this classical setup is that like simple functions, which you can say are like polynomials of degree lower than d, form a measure zero subset of parameter space, right? Because to get something of less than degree d, that final coefficient would have to be zero, and that happens with measure zero. Okay, so for this class, parameter space is a really like really accurate model of the space of functions. It's one-to-one. Simple functions are like a small subset. And this is lovely, but it's not very far from being the case in these families that we've been talking about. So for the remainder of this talk, I'm going to resume talking about the family of neural networks that we've been talking about throughout. That is fully connected feedforward neural networks with ReLU activation functions. So we're keeping architecture, and this whole setup. I won't go through it again. So here's an example of like a toy architecture. I like this one because it's kind of the simplest one where interesting things start to happen. So 1, 2, 1. So this is maps that go from R1 to R2 to R1. In this case, the parameter space is R7. So if you write the parameters like the coordinates, the parameters is A through G. The map from R1 to R2 has this form, and then you do a combination, and so the total map is like this expression.
Okay, so in this sort of toy situation, our parameter space is 7-dimensional. Sorry. Pause for a second. Okay. All right, so let's just kind of like explore an example. So we're in this architecture. We've got parameters A through G. And if we start just kind of imagining what these graphs look like, if we pick A, B, D, E, and G to be all negative, you know, you can say that, okay, we send X, the first coordinate will be sigma of AX plus B. Okay, if A is negative and B is negative, it'll be like that line, and then the ReLU makes the -1, 0, and it looks like that. And then similarly, if C and D are as above, the graph will kind of look like that for the other coordinate. Then when we add them together using E negative, F positive, G negative, okay, we get something that looks like this dotted one, but then you do the ReLU and we get the, okay. So the total function takes X and it sends it, the graph looks like that. So now we ask ourselves, what if we use slightly different parameters? Like this is for some particular value of A through G. But if I just like perturb those values a little bit, like what could happen? Right? Like this is pretty stable. Really, there's only 2 things about this graph that I can change under really small perturbations. Basically, I can change this point where it bends, and I can change the slope of this line. So even though there's 7 parameters, like locally, under small perturbations, there's really only like 2 dimensions worth of function. Let's do another. Yeah, okay, here, I said that. So we've got 7 parameters, but there's 2 ways, like locally, to change the function. And this is also true for all the parameters that are near this particular one that we're looking at. So what does this tell us about the fiber? Right? We've got 7 dimensions of parameters, but we really only got like 2 dimensions worth of functions. So that means that there's 5 different directions in parameter space that essentially don't do anything at this point. So not only is the realization map not injective, it's like really not injective. There's a 5-dimensional space of parameters that are all going to give you exactly the same map. Let's do a different parameter. I'll call this one theta1 for the exact same architecture. So again, we've got parameters A through G. We pick some A through values. Okay, so I don't know, we pick A, B, and C so that the graphs look like this. And then you add them together and you get something like this. Okay, so same architecture, just different parameter. And now ask, how many things about this graph can we change by perturbing our parameter? So if you look at this, honestly, the first time I looked at it, I was like 6. There's 6 because there's, I don't know, 3 pieces. But no, the answer is there's really only 5 things you can change independently. Which 5 things you want to pick is up to you. Maybe I'd pick like maybe what these 2 points are, P1 and P2. Maybe I'd pick like the slope of this one and the slope of this one. But then the slope of this middle one is actually the sum of these other 2 slopes. So this slope is just this slope plus that slope. So you don't get to pick that one. And then maybe there's like a y-intercept. So basically, like, there's 5 things I can change independently. And this is true for all the nearby parameters too. So near this parameter, fibers of the realization map are 5-dimensional. Wait, 2-dimensional. Sorry. 7 minus 5. 7 minus 5. 2-dimensional. 2-dimensional. There's 5 dimensions worth of things you can change. There are 2 dimensions that don't do anything. Okay, so this is kind of summing up what we can learn from this little pretend experiment that we did. So first point, in different parts of parameter space, fibers have different dimensions, right? Because we saw one where it was 2, one where it was 5. So another sort of more concise way to say this is that the degree to which the realization map fails to be injective is very inhomogeneous across the parameter space. Okay, so I guess the flip side of that, point 2, is that some functions are realized by a very high dimensional subset of parameters, others by, this should say a lower dimensional subset. Oh, it's here. It's here. I just moved it down. Okay. So this is already kind of interesting when you think back to this question of like, which functions are we likely to select when we're training, right? Because we're now realizing that some functions they're represented by a lot more parameters. So we're going to be more likely to pick those, maybe? Okay. So this is just a comment that the space of functions realized by an architecture is not a vector space. Right, so vector space is closed under addition, multiplication by constants. Yeah, I guess that's it. So how do I say, okay, so the space of functions you get from an architecture, it is closed under multiplication by constants, but it is not closed under addition. And one way to see that is that there is some maximal number of cells that your complex can have based on the architecture. If I take 2 different functions that both have that maximal number of cells and I add them together, I will probably get something with more cells. And that's too many cells. So it is not closed under addition. So it's not a vector space, which is interesting, but it also means that like all the things that you can do when you have a vector space, you can't really do, like nice metrics, like L2 metrics. It's just makes it a little harder. So, right, not only is it not a vector space, we don't even have a nice way to say what the space of functions is. So given an architecture, what's a nice characterization of exactly which piecewise linear functions can be realized for that architecture? So given these sort of challenges, how can we define the dimension of the space of functions that can be realized by perturbing your parameter? I'll come back to this question later. Okay. Questions before I keep going? Yes. Yeah. The expand on like, oh, well, so just, yeah, why did I put, your question is why did I put quotes around the word dimension? Yeah. So it's because like, we know what the dimension of a vector space is. It's the number of linearly independent vectors in a set that spans or something like that. But if your set is not a vector space, it's just like, what does it even mean to say dimension? So that's all I was trying to say there is like, there is some intuitive notion of dimension, like, and we were talking about it here, like the number of things you can change, but that's different than, you know, the notion of the dimension of a vector space. So in one of the later sections, I'll kind of say one way to describe that. Yeah. Other questions? Yeah.
Kind of a certain critical point here, like where theta is close to fibers of certain dimension and also the other dimensions.
So what I'm going to say later is I'm going to talk about a little bit about how parameter space breaks up into these regions where the fibers have certain dimensions. But really the question of like how those regions sit next to each other is like totally open. All right, so topic 3, batch fibers. So far, when we've been talking about fibers, we've been talking about like making the functions be the same function everywhere on the domain. That is like two parameters are in the same fiber. If well, theta 1 and theta 2, if the functions are exactly equal for every single x in Rn0. But we might not necessarily care about every x in Rn0. We might only care whether the functions are the same, whether they coincide on some subset of Rn0. So that is, given a particular subset, Z, you can ask, is it true that two functions agree for every point x that's in that subset Z? So this is what we would call, in this case, we call it the batch fiber. So why might we not care about all of Rn0? Well, a couple reasons. Well, one is like maybe Z represents the data that you have, your training data. You definitely don't have all of Rn0. You have some finite set. So, and like when you're computing your loss function, you're trying to do this training process, all you have is some set Z. You don't have anything else. So maybe studying functions that agree on a particular subset could be helpful for understanding training. More generally, there's something that people sometimes call the data manifold hypothesis, which is basically just the statement that in whatever phenomenon you're studying, the like space of possible reasonable inputs to your model is probably not all of Rn. It's probably a submanifold. Like imagine we're thinking about like images of n by n pixels. If I just randomly assign like a value to each of the pixels, I'm probably not going to get a picture that you would ever encounter or need to think about. So really maybe asking, so this is the assertion that like your data probably lies in some submanifold. It's not a technical thing, but just the idea that you don't need all of Rn0. Okay, so for these reasons, let's just look at when functions agree on a particular batch of points. So here's the definition of a batch fiber. So given a batch, but I just mean some subset of your domain, we'll say that the Z batch fiber for some function is, well, here's my notation, but it's the set of parameters so that the function agrees with G for all the points in your set Z. So rho is my realization map. Rho inverse was the fiber everywhere. And when I put a subscript Z, it means I only care about whether they agree on a set Z. And this was just rewriting that using like different notation. This is the function restricted to the set Z is equal to the other function restricted to the set Z. Okay. So something that I proved recently is this theorem, together with my collaborator Ellie Grigsby. So fix any architecture of these feed-forward ReLU neural networks, and then fix any finite set Z in your domain. So the conclusion is that for almost every, meaning everything outside of a Lebesgue measure zero probability, sorry, a Lebesgue, Lebesgue measure zero set, outside of a measure zero set, you can choose coordinates on a little region in parameter space. So I'm going to call it a neighborhood U of your parameter, so that it looks like this. Essentially, there's like, I would call it a fibration. So here's your fiber in blue. So that's this right here, the fiber with respect to Z, and then in the other part of the coordinate, it's just the other coordinates. So this is like, if there's 5 ways to change your function, these things would be 5-dimensional. And then if there's like 2 dimensions in which your function doesn't change, these would be like 2-dimensional. Yeah. So this is for almost every parameter. And it depends. So in here is the assertion that for any set, for almost any parameter, the size of the fiber is sort of locally constant. Yeah. Oh, so this is a there exists statement. The way we stated it is that there exists. The way we proved it is slightly more constructive. It uses the open rank theorem from like smooth manifolds, which says that if you have a map that has a constant rank that's smooth on a smooth manifold, that you can define coordinate charts that yeah. Can I state the smooth constant rank theorem? No. No, that you can define coordinates. You can define a coordinate system where basically what the function does is just like you can see it directly in the coordinates. And so yeah, we build it out of that theorem. So it's like somewhat constructive. I can say more about it, but yeah. Okay. So in that theorem that I just mentioned, the measure zero set where the theorem does not hold is basically, it's like parameters where which cell of the polyhedral complex contains one of your points changes. And so this is an example of this phenomenon. So back to our 1, 2, 1 example. So imagine I've picked points Z1 and Z2. Oh, sorry, this is not 1, 2, 1. The only thing I'm going to allow myself to do, oh no, this is my 1, 2, 1 example. Yeah. Yeah, this is my 1, 2, 1 example. So here, the polyhedral complex has 2 1 cells. There's like this 1 cell and there's this 1 cell. And in this case, Z1 and Z2 are in the same 1 cell. But if I just shift my graph up a little bit, I think that was corresponded to changing the parameter G earlier. If I shift it up a little bit, and this is like showing the impact of the ReLU, then all of a sudden we have the combinatorial structure changes. Now we have 4 different 1 cells. There's like one 1 cell here, one 1 cell here, another one, and then another one. And now Z1 and Z2 are in different 1 cells. So somewhere between these two, there's an intermediate parameter where the combinatorial structure changes. And those are the parameters that form this measure zero set, where there's sort of like the walls between the regions where we have these different dimensions. I mentioned this conjecture earlier to someone. Open question. Prove that for any architecture, the set of combinatorially stable parameters has full measure. So combinatorially stable would be like
where perturbing it does not change the structure of the complex. And I don't know. We wrote a precise definition of what that means. I mean, I think it's true, but it'll just take some work to show it. Okay, so a corollary is that if you have a parameter that's combinatorially stable, then a little neighborhood of that parameter looks like a full fiber cross however many more dimensions you need. Okay. So here's a very vague open question. How is parameter space made up of regions of this type, where like locally fibers have the same dimension? And how do these regions sit next to each other? So for example, can you have a region where you have 5-dimensional fibers? Can that be next to a region with 100-dimensional fibers? I don't know. Yeah, anything that you can prove in that direction would be great. Questions? Great. Okay, so fibers exist. They have different dimensions. What do they look like? So open question. Topologically, what do fibers of ReLU neural networks look like? So I have some examples of interesting fibers. Here's an example. Back to my favorite architecture. So consider the function, so 1 to 2 to 1. So 1-dimensional input, 1-dimensional output. Consider the function x goes to absolute value of x. So which parameters give you this function? My claim is that the fiber is disconnected. So I think this is kind of, okay, so it's just like kind of already interesting when you start to think about training. It's telling you like, there's some way to, there's this function that maybe I'm interested in, and maybe I can get to it over here, or I can get to it over here, but like not in the middle. So let me prove that this is a disconnected fiber. Okay. So here's our function. X goes to, right, and there's our first one, our second one, and we take linear combination. Yeah. So suppose we have A, B, C, D, E, F, and G, so that this is the function x goes to absolute value x. Let's figure out what those parameters A through G have to be. So our first observation is that this function, where is it nonlinear? Well, it's nonlinear exactly when the ReLU sort of kicks in. And so that happens when either Cx plus D equals 0, or when Ax plus B equals 0. So it's nonlinear at exactly the 2 points, x equals negative b over a, or x equals negative d over c. How many points of nonlinearity does this function have? How many points is the function x goes to absolute value x not linear? 1, thank you. This seems to have 2. So if they're in fact the same, these 2 points had better be the same points, negative b over a and negative d over c, and they had better be the point 0. So, right, one nonlinear point at 0, so we must have this equation. 0 equals negative b over a equals negative c over d. So we can conclude from this that our parameters must have b equals d equals 0. Okay. Great. So now we know that our function has to look like this. I've just set b and d to be 0. Okay. Well, we know that this is supposed to be the function x goes to absolute value x. And so we got to have 0 goes to 0. So that means that our g must be 0. Okay. Now we know our function has to look like this. I've just gotten rid of the g. So what is this? This is a composition of, well, there's sigma, and then
I'm claiming that this is this function. Sigma is non-negative. The function that we're claiming that this represents is non-negative. So the only way that could be true was if E and F are both positive. Okay, so we've got E and F are positive. Great. So now we've got two possibilities, right? Remember, we're trying to get the function absolute value of x. And if you look at sort of the slopes given by this, the two slopes are there's like a part where the slope will be E times A, and there'll be a part where the slope is F times C. So there's like two possibilities. Okay, so what we've boiled this all down to is that if we have a parameter A through G that represents this function, it's one of two types. It's either in this set or it's in this set. And if you think about these two sets carefully, or maybe not even that carefully, these are all the same. These are different. These two sets are non-empty. They do not intersect. So therefore the fiber is disconnected. Question. For which architectures and which functions is the fiber disconnected or connected? This is literally the only example I know so far. We didn't try very hard, but we found this one. So which ones? Okay, so connectivity, that's like the most pretty basic topological property. Just more generally, what do fibers look like? Are there architectures and functions where fibers have non-trivial quality? If so, how often does this happen? I haven't found an example yet, but maybe you guys can. Questions? Yeah. Yeah, definitely. I mean, have I done it? No. Do I believe it could be done? Yes. Okay. So great. So far, what we've kind of been talking about is the fact that basically that our parameter space is not a very good model for the space of functions. Because the map is not injective that sends parameters to functions. So like it's not faithful. It doesn't represent it very well. So, but we do our gradient descent, our training on parameter space. So it's kind of natural to wonder, like, could you sort of like quotient out by fibers? So could you take parameter space and just form a quotient space by saying that let's build an equivalence relation where two parameters are related if they're in the same fiber? Unfortunately, this doesn't work, or at least it doesn't work without some complicated stuff going. It doesn't work quite. So let me tell you why it doesn't work. So here's a specific architecture. The architecture 1-1. Literally the most boring thing possible. So this is x goes to sigma of ax plus b. Here's a claim. So our parameters are a and b. There exist two different points in parameter space. One is a1, b1, the other is a2, b2, such that they give you the same function. In fact, what they give you is the zero function. But in a little neighborhood of your first parameter, there's some parameter that gives you a function that you cannot get near the other one. Right, so like here's one parameter. I maybe didn't say that very clearly, so I'm going to draw a picture. Here's theta 2. It says that no matter how small a little neighborhood I pick, I can find something in here that gives you a function
that is not in this little neighborhood. Okay. So basically, like, you can get the same function from multiple parameters, but what functions you can get nearby can be different. And so this is an obstacle to what I really wanted to do, which was like take a quotient. Because what it's saying is that parameter space is not naturally like a covering space of the space of functions. Like, it doesn't lift well. That was a bummer. So could we fix this? Maybe. Maybe there's some way to take like a more subtle quotient. I don't know. So, okay. Yeah. Before I go on, questions, thoughts, comments? Yeah.
Is this behavior due because of the event, or does it happen if you take another activity?
Like this specific like problem about being a quotient? I've only thought about it for ReLU. I don't know if it works for other functions. Yeah. All right. So I'll move on to another piece of this story, which I call functional dimension. So I advertised this earlier in the talk. The question was, how do you define the dimension of the space of functions that you can get by perturbing a parameter? So this is an answer for how you can define dimension. So first, I want to define the evaluation map. So fix a finite set of points in your domain. I'm going to call it Z. I'll call the points Z1 through ZK. The evaluation map, I'm going to call it E for evaluation map, and then Z is denoting the set of points. Goes from parameter space to ND is the dimension of your output space. You have K points, and so it's ND times K. And all it is you just you make a list of what the function f theta does at each point of your set Z. So the idea here is that like you're using this finite set Z to sort of probe the space of functions. Like this isn't the function, but I'm recording what the function does at specific points, the points Z. So, right. So if I want to understand F, it's basically like, let's try to understand the restriction to the set Z. Happy with the definition of the evaluation map? Yeah. Oh, okay. Okay. For simplicity, as I go forward now, I'm going to take the output dimension to be 1, but it'll all be the same theory. It's just a little nicer to write. So my functions will go from Rn0 to Rn1. So question, how many linearly independent ways can you perturb or can you change the evaluation map by perturbing your parameter? So, I mean, this is just a vector of numbers. And so we know how to figure out how many linearly independent vectors we have. Like, that's something we can actually compute. So the idea is to use these approximations to get the dimension. Okay, so that's the question. We fixed the set Z. How many linearly independent ways can we change this data? Well, one way we can do that is we can take the Jacobian derivative of this evaluation map. So, right, so what's the Jacobian derivative? I always have to remind myself. So in this case, EZ is a vector valued function. Theta has a bunch of parameters, coordinates. Its coordinates are theta1 through theta d. And so the derivative of this map is this matrix whose rows correspond to the different points, Z1 through ZK,
and whose columns correspond to the different coordinates. And what you do is in each entry in this matrix, you ask, what is the derivative of the evaluation map at that one particular point with respect to, in this case, the first coordinate of your parameter. And then you do this in all the different coordinates. So in this first row, I record basically the impact on what the function does at the point z1 of perturbing each of the weights and biases. And then I do that for each of the different points. Did you have a question? Mm-hmm. So you're saying that, oh yeah, so if this is, right, yeah, so if you're saying if k is smaller than d, then the rank is going to be at most k. Yeah, I agree. I'm gonna come back to this. It's a good observation. Yeah, right. Okay, right. So the rank of this matrix is exactly, it's like telling you how many different ways can I vary these vectors. Right, because like if this row is like say twice the next row, then like there's really only like, it's like you're really only changing one thing. Right. So starting to get at your question, or which you're pointing out that what your batch z is like really matters, right? If z is less than k, this rank is going to be less than k. Yeah. So first, I'm leading up to defining functional dimension. First, I want to define batch functional dimension. So this is the batch functional dimension for your parameter is, for the batch z, is this rank. So it measures the number of linearly independent ways to perturb what your function does on the set z. Okay, but as you're pointing out, right, this really depends on the set z. So what can we do? One thing you can do is take the supremum over all the different sets z. So now I'm going to define the functional dimension. It is, so I'm going to denote it dim fun, functional dimension of my parameter theta. So it's like you pick a set z, and then you compute this rank. And that gives you something. But then maybe pick a bigger set z and compute the rank. And then pick a bigger set z and compute the rank. And it's like the biggest possible rank that you can get. So it's like you're sampling what your function does at just like more and more points. And so you're allowed to sample at as many points as you want. So this quantity is sort of measuring like the number of linearly independent ways to perturb the whole function. Yeah.
We said that C forms or it's too similar to the main form of error zero, but have you tried to just restrict that condition of the brain of the set error zero to only to main form to see what happens?
I have not, but right. So your question, I'm just going to say it again to make sure I understand. You're saying instead of considering z's that live in Rn0, like maybe our data actually only lies on a submanifold. So why don't we only sample z's from the submanifold? Yeah. Yeah, that should be done. I've not done it. Yeah, other thoughts or questions? Yeah. Okay. I drew these little asterisks, and then I said asterisk, a slight lie. I'm hiding something. What am I hiding? Anybody know what could go wrong with what? There's something that could go wrong here. Thoughts? Right, so what am I doing? I take these points, I take the derivative.
Yes, that is what I'm hiding here. When I'm taking to take the derivative, these functions need to be differentiable. But we're talking about things where there's like a lot of nonlinearity, like piecewise nonlinear. So it's not differentiable everywhere. So that's the detail that I was hiding. Yes. Yes. And that's what I was going to prove, or that's what I was going to say next. So good job. Yeah, right. So we need the function to be differentiable at your parameter theta for at every z. So you could call a point parametrically smooth for a parameter theta if the derivatives actually exist, if it's differentiable with respect to theta there. So in our definitions on the previous slide, what I didn't write, and like the additional detail, is that we have to assume that these sets Z consist of parametrically smooth points. Right. Now, how many points are parametrically smooth? Almost all of them, and here's why. So maybe before I say why, I'll say it's useful to think of our function, our parameterized class, in a slightly different way. So instead of thinking of f as a collection of functions from Rn0 to R, think of the family f as a function from the product space to R, where like, what does it do when you give it an x and a theta? Well, what it does is it does the function f theta evaluated at x. Yep. No, they're not. I mean, it's going to be like the nonlinearities are they're kind of nice nonlinearities. Like they're like that kind of nonlinearity. So like there's some way to make a notion of derivative, but it's just not. We didn't define it. Oh, yeah, there's ways to take the derivative. Yeah, it's a good point. Okay, so lemma, if you think of this as like a map from the product space, this is a piecewise polynomial, meaning that like this whole product space, you can cut it up into pieces, and there's like the restriction to each piece is a polynomial. That is, there is an algebraic decomposition of this product space into cells. The cells are semi-algebraic sets. Semi-algebraic just means they're defined by algebraic equations, but you're allowed to use inequalities. Like, this algebraic expression is less than or equal to 5, for example. That's what makes it semi instead of just strictly algebraic, which would be equals 5. Okay. So the bent hyperplane arrangement and this polyhedral complex that we saw for a specific parameter theta, one way you can think of that is that it's just a slice of this cellular structure on the product space. Right. So the boundaries of this cellular, like the lower dimensional cells, are where the complex kind of changes. The parameters are not combinatorially stable, and they're defined by algebraic equations. Algebraic equations have measure zero solutions. So hence, the set of parameters where you can't take derivatives is a measure zero subset. And not only is it measure zero, but it's like a nice union of algebraic submaps. So you anticipated that's what I was leading up to. The statement that almost every parameter or every point is smooth. So this is from a paper that is joint with Ellie Grigsby and David Rolnick. And this is
the result of an experiment, trying to figure out how does functional dimension vary across parameter space. So here we use networks of depth 4, and there's different widths, 5, 10, and 15. And so what we did is we just randomly picked a lot of parameters, and we computed the functional dimension of those parameters, and then we made a histogram. So like if we look at depth 4, width 5, that's these blue guys, you can see that like most of them have like a big functional dimension, but there is this drop off. Some parameters have a lot lower functional dimension. If you use depth 4, width 15, again, most parameters have like a big functional dimension, but some have a lot lower, and the tail is kind of a little bit more spread out here. If you go to depth 6, the pictures kind of change. So here the peak was to the right, meaning like most parameters have like the biggest possible functional dimension. But in depth 6, the peak is kind of in the middle. So it's actually saying that like most places in parameter space, you do not get the top possible dimension worth of function. And in fact, that gets even more pronounced if you go over here. This is networks of depth 6, width 15. You see that some have the biggest possible functional dimension, but like most of them do not. So the observation, okay, so right, what is this showing? It's showing that functional dimension is very inhomogeneous. It's showing that the effect is more pronounced for deeper networks, meaning like more layers, right? And it is less pronounced for wider networks. That one's maybe a little less easy to see, but at least there's some sort of evidence that like this actually is an important phenomenon. It happens a lot, and it's related to depth and width. Questions, comments? So you might wonder, like, what causes functional dimension to drop? Well, we did that sort of example earlier with 1-2-1 architecture, where we found like a 5-dimensional fiber and a 2-dimensional fiber. So we kind of saw, but how else can it drop? So these 4 pictures are 4 different ways functional dimension can drop. This is not an exhaustive list, but like, for example, in this first one, the yellow is meant to indicate the image of the domain in some hidden layer. And the blue is a hyperplane associated to the next layer map. If you imagine that the positive side of this hyperplane is like down here, basically all of this becomes 0 with respect to that neuron. So it's basically like all this structure just like doesn't even matter from the point of view of this neuron. So like that's the way that like all the parameters that went into building this structure like just don't even matter in the end. And there's some other ways that you can do this. For example, if you have 2 neurons that are active but they're never active at the same time, that causes it to drop. And there's some other mechanisms as well. I maybe won't go into all of them. Okay, so I think this is actually my last slide. And this is about something I'm thinking about right now, work in progress, which is how functional dimension changes over training. So when you initialize your training, you initialize randomly somewhere in parameter space, and you can compute the functional dimension there. And then as you do this training process, you can ask, how does the functional dimension change? And so this is just 2 different like experiments and 2 different data sets. They're toy data sets that come built into the package scikit-learn in Python. The left one is about the prices of houses in California. It's like, I think it goes from like R8 to R1. that is like, there's like 8 attributes, like, you know, the size of the house, the number of bathrooms, I don't know. And the output is the cost of the house. The other data set that I played with is a data set consisting of images, and they are 8 by 8 pixels, and they're grayscale, and they're handwritten digits. That 8, 1, 2, 3, 4, 5, 6, 7, 8. You know, and they're colored in grayscale, representing digits. So, like, you know, maybe that's the digit 0. So this one is not MNIST. It's because MNIST is it 16 by 16? 28 by 28. Yes, this is like smaller. It's like 8 by 8. It's just so that I could run it really quickly on my laptop. So in this case, I set up a training thing where I asked it output a number 0 if it's a 0, output a 1 if it's anything other than a 0. And so in both, I just did some training and computed functional dimension. So on the left, what this plot is across the bottom, this is the training, the epochs of training. And so when we initialize, functional dimension looks like it's like about 125. And then as we train, so this is the loss goes down, and the functional dimension just kind of keeps going up. But you can see that like there's definitely like a connection, right? Like these graphs, you can kind of see one graph in the other graph. So what this is saying is like we're moving through parameter space, and we're moving into regions where you have more and more expressive power in some sense. Like you can achieve more and more functions in a small neighborhood. This one is pretty different. In this one, this is the digits one. We initialize somewhere randomly, and it looks like when I initialized, the functional dimension was like 800 or something. And as we train, okay, the loss stays kind of constant, and the functional dimension keeps going up, and then it peaks. And right at about the time it peaks, the loss plummets. And then it kind of, continues to get a little bit better. So like what I think is going on in this picture is that essentially as you're training, the training process is like I think of the parameters as being like levers. It's like it's turning on all of the levers because it's trying to figure out it's not trying to do anything, it's just the algorithm, but in some sense it's trying to figure out what are the important levers, and so it just turns everything on, and then it reaches a point where it's figured out which ones are the important ones, and then it can fit the data really well. So 2 different behaviors. I don't really understand why they're different. I have some conjectures. I'll tell you what my conjectures are. In this case, the data about housing, it kind of fills up the space. Like it's only 8 inputs, 1-dimensional output, and like there's kind of a lot of randomness in it, right? Like it doesn't perfectly correlate. That is, the data does not lie on a lower dimensional submanifold. Or if it does, it's not that much lower dimensional. Whereas this one, images, I think the data probably lies on a low dimensional submanifold because like you can't get any picture. So I think somehow the fact that the dimension just keeps going up and up is kind of reflecting the fact that you're trying, that your data, that your data is really complicated. I'm not saying it well. That your data fills up a lot of the space, whereas in this one, your data is a lot lower dimensional than the ambient space. That's my conjecture. Yeah. Yeah. Yep. This is literally all I know right now. Yeah. Good question. Yeah. Say that again? Like, yeah, this was about looking for digits that are 0. This was about the price of houses. Yeah. Yeah, sorry, they're like 2 totally different data sets. Yeah, this one is about predicting the price of a house in the US state of California. This one is about recognizing digits that are 0. Yeah. Yeah. It's a classifier, but I turned it into a regression question by saying that any digit that's a 0 goes to a 0 and anything else goes to a 1. Well, yeah. Well, it's trying to predict 0 or something other than 0. So, like, I'm asking it to predict predict a number in the interval 0, 1. Yeah. I'd say it's a classification question turned into a regression. Yeah, I don't know, somewhere in the middle. Yeah. Other thoughts or questions, comments? Yeah. The what is? Oh, I took my data and I split it into a training set and a validation loss. Validation. Yeah, the red is the test. Sorry, the blue is the yellow. I know my colors. Yellow is the data that I was training on, and yeah, red is unseen data. I called it val. I probably should have called it test. Yeah.
The effect is the neural network is
over parameterized, overfitting.
Overfitting?
Yeah. 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 Sorry. Okay, I think that. Yeah. So these are like pretty small data sets. Like they consist of like, I don't know, like on the order of like 2,000 data points or something. So like I made these pictures, I think on Google Colab in like a couple of minutes. Yeah.
You try with different those functions?
No, no. This is all I've done.
There's a method like optimization, how many layers
Oh, the question like which? It's a good question. Yeah, yeah, change the size. Yeah. Yeah, yeah.
It's, for example, there is no relation between too many layers and overfitting.
There is, right. I mean, like the more complicated your architecture is, kind of the more likely you are to overfit. Yeah, the more layers and the wider. Yeah. Okay. So I think, yeah, that is my last slide. So stop here. Thank you all.
Okay, thanks. And if you don't have more questions or comments, we need to say, I want to say thank you to Kathryn Lindsey because of this course. We know that you made a lot of effort to start here. Then thanks. Please thank again to Lindsey.
Oh, thank you. Well, thank you all for your attention, for all the excellent questions. And like, it would make me really happy if some of the people from this conference finds any of this inspiring and end up doing something based on any of this. So please consider this like an invitation. Okay, thanks.